Hello, I'm Dr. James Dborin, Head of Research at DoubleWord AI, and today we're continuing our series of videos on tips and tricks for self-hosting large language models. And today's video is going to be how to make your load balancer LLM aware. In our map of topics that you need to care about when self-hosting language models, we're going to be covering things from the field of optimizations, as well as orchestrations over here. So today, we're going to cover three things. We're going to cover first, why you should care about load balancing at all. We're going to cover why traditional load balancing fails when it comes to LLMs. And we're going to look at how to build an LLM-aware load balancer that fixes those problems. So why should we care about load balancing at all? Well, this is quite a simple question to answer, but first maybe we'll talk about what load balancing is. So typically, when I'm load balancing, I have some set of applications that are horizontally scaled across many nodes. Each application gets its own computer. I have some load balancer, and the load balancer receives a request from a user, and it decides it's going to send this request to one of the three identical copies of the application that are each running separately. So maybe it chooses this one, and then when another request comes in, perhaps it chooses this one. Another request comes in, it chooses this one, and the goal is to evenly distribute the load across multiple applications so that no one application is overloaded. And why do we care about this? Well, if we sent a bunch of requests to the same application or an application that was busy, then the users of that application will see slower response times. The application can't process their request straight away, and you're paying for compute resources that are completely idle. If I had a bad load balancer that was only ever sending requests to one of these two applications, I'm paying for compute resources for this one, but it's not actually helping me deliver a good service to my users. So it's obvious why we want load balancers to be effective. If they weren't effective, we'd be wasting money and delivering a worse service to our users, and that's not a good thing. So let's look at some strategies for traditional load balancing and why they start to fail when we're talking about load balancing between copies of large language models. So we're going to consider a load balancing strategy called the round-robin strategy. In the round-robin strategy, I have my load balancer, and I have my three applications, each running separately. And in the round-robin load balancer, I'm going to first send the first request to this first app. And then when a second request comes in, I'm going to send it to this copy. And when a third request comes in, I'm going to send it to that copy. And then when a fourth request comes in, I'm going to loop back round and send it round to this application here. So this is quite good at just distributing the load of applications evenly, the load of requests, across the applications. So when would this start to fail? So this load balancing strategy will fail when there's some uneven compute requirements for each request. So if request 1 takes a really long time and requests 2 and 3 are really short, then by the time the fourth request comes around, maybe request 1 is still processing in application 1, but requests 2 and 3 are done. So request 1 might be a long request, and request 2 and 3 might be a short request. And so when the fourth one comes around, 1 is still processing, but 2 and 3 are free. And so an ideal load balancer would send the request either to application 2 or application 3, but it wouldn't send it to the first one. And this sort of situation happens in language models all the time. So for example, if you're using a reasoning model or some other model that, or you have like a RAG application deployed, there are certain requests that are very, very expensive, ones that require very long reasoning chains. For example, if you've ever used OpenAI's O1 series, sometimes it will think for 1 or 2 seconds for your request, sometimes it will think for minutes on end, and you can't really predict that in advance. And if you're doing something like RAG, then Sometimes you have a very long context that requires a lot of information, tens of thousands of tokens, and sometimes a user will just send a request like, what is your name? In which case, maybe nothing gets pulled in and the model just answers without a long context. And so in those situations, you can have long requests and short requests, and the long requests in a round-robin scenario might end up piling up within a single application, meaning that your users wait longer than they want to. So how can we fix this scenario? Well, ideally, we would like to have a sense of how busy one of these applications is at any one time and use that information when we're load balancing. And we can do that traditionally by using metrics that are reported from those compute instances. So what is commonly used is things like CPU utilization, maybe memory usage, and if you're working with GPUs, you might use something like the GPU utilization that's reported by NVIDIA SMI, or you might use the VRAM usage or something like that. So let's go through these one at a time and see why these don't work with language models. So these first two, the issue is that if you're doing inference of a language model, for large chunks of the time, the CPU is idle. Most of the processing happens on the GPU, with only occasional round trips to the CPU to push the next request onto a queue for what work the GPU should do. And if you're using something like CUDA graphs, that's pre-recorded, and so many steps can be performed on the GPU in between commands sent by the CPU. And so even under extremely heavy load, the CPU utilization or memory usage might be quite low. And so this stops being a reliable metric when you're doing a lot of GPU workloads. So the issue is that it's uncorrelated to GPU load. And the GPU load is really what we care about in this case. So instead, we can use these metrics that are reported by GPUs. But often these don't work either. So for the GPU utilization that's reported when you run a command like NVIDIA SMI is telling you more how often something is being done on your GPU. It slices the GPU into time slots, and it reports the percentage of these time slots where some work is done on the GPU. But that's not particularly useful in this case. For example, if you are running a model that can support on your GPU a batch size of 128, if you run at batch size 1, you're still likely to report a really high GPU utilization because stuff is running on the GPU. It's just that it's not maxing out the compute capacity of that GPU. And so you might say, I'm running at 1% capacity. I have one request that could have 100 requests, but your GPU utilization will still be very high. And so that's not very useful. And a similar thing is true with VRAM. It's often the case in most inference engines that you don't dynamically allocate memory on the GPU such that it's busier when it's higher when it's busier and it's lower. Otherwise, typically you pre-allocate the entire KV cache on the GPU and model weights on the GPU. So you're typically reporting close to 100% VRAM usage at all times, and you're just managing that memory. You're not creating new chunks of memory. So in both these cases, it doesn't scale very well with load. And so these would typically be the things you use to make these load balancing decisions, but none of them work. So what can we do? Well, if you want to make your load balancer LLM-aware, then you need to pick some metric which is tightly correlated with the load on the system. And one such metric is the KV cache utilization. So let's quickly look at what a KV cache is. So a KV cache is a big chunk of memory, which I'm going to represent with just a big box with these slots of memory. And each slot in memory represents a single token. So each of these little boxes will have a token allocated to them. I'm going to use a different color for each user. So in this case, maybe I have user 1 who has in total processed 6 tokens. User 2 might have processed 3 tokens. And this user 3 might have processed 4 tokens. So in total, my LLM is dealing with 13 tokens, and every empty token is one that is spaced for another token that can be processed. So in order for a request to be processed, there needs to be space for it in the KV cache, and there needs to be space for its generation as well. So if you want to send in 8,000 tokens and receive back 10,000 tokens, you need at least 18,000 tokens free in the KV cache for that particular request. And so this is the sort of optimal metric for making load balancing decisions on, because you can directly say how full an instance is based on how many tokens it's currently processing and the capacity it has for processing tokens. So if we go back to the example we saw before with some load balancer, and we have 3 copies of the same language model. And in this case, I'm going to say that each language model has a KV cache with a certain fullness. So this one is 70%, this one's 20%, and this one's 30%. This sort of reflects what we said before. Maybe this first one has dealt with a long RAG request or a reasoning request or something like that. That means a lot of tokens got used by a single request, and the others haven't faced that. They face short requests. So in this case, when a new request comes in, it makes sense to send it to one of the 2 applications that have a lower KV cache utilization. They have more free tokens, so it's going to be processed immediately, as well as the fact that it's going to be able to accept the more users' requests after this, with these KV caches being empty. So it's going to send it to one of these 2 applications. So how do we get this information out of the LLM? Well, typically it requires some sort of reporting based on the inference engine. So there are a bunch of different inference engines out there. We at DoubleWord have our own one. There's VLLM, there's TensorRT LLM, there's SGLang, there's a whole bunch. And it requires that your inference engine reports this metric so that you can make load balancing decisions based off of it. So you need to deploy some sort of metric collecting tool that watches these applications, watches them report their KV cache percentage, and then the load balancer uses this metric system in order to make its load balancing decisions. This is also done, for example, by NVIDIA's Dynamo system, where they go in and edit some of these inference engines to make it work, and it's done by DoubleWord in our inference stack as well. So KV caches aren't the only thing that we might want to make LLM aware in our load balancing system. There are other ways of estimating the cost of a request. So for example, with a KV cache, it is not always the case that every unique token in the requests, or that every token in the request gets a unique slot in the KV cache. So for example, let's say we have some request, and now the colors don't refer to users anymore. I'm going to use the colors to refer to some sort of shared prefix. I'll explain in a second. Let's say we have 2 requests that have the same set of 5 tokens at the start of the 2 requests. This might happen if you have like a long system prompt, for example, explaining the application that the language model is being used in, some rules for its generation, tools it has available to it, things like that. You can get quite long system prompts that get prepended to every single invocation of the language model. So in this case, we have 5 tokens that are shared at the start of every prompt, and then request 1 has these 3 additional tokens, and request 2 has these 4 additional tokens. What you will notice is that in the KV cache here, we actually duplicate these tokens. Like you can see here, we put them in twice, but this is unnecessary. It wastes space as well as wasting compute. A more optimal way to do things is to only record this token, this set of tokens, this prefix once, and then simply refer back to them when computing the next request and keep these in a single slot in the KV cache memory and reuse them over and over again. And when we do this, it means that requests with very long prefixes can be very fast. You don't need to pre-fill the 20,000 tokens in your system prompt. You can just pre-fill the 100 tokens in the user query that gets added to the end of it. And so this can really improve things like time to first token, for example, or like context speed for, or time to first token for long context examples. And so how can we add this into our load balancer? Well, what the load balancer can also do is it can look at the request. So I'm going to do a similar thing as before. You get a request with this long system prompt, and it can look at your various versions of the model, and it can identify that that this third application here has in its KV cache a big overlap with your incoming system prompt, indicated by it sharing all 5 prefix tokens. So this currently exists in the KV cache, so it doesn't need to be pre-filled. Application 2 has some overlap, but a smaller overlap, and application 1, the one on the highest load, actually has the lowest overlap. And so in this case, your load balancer can make a decision like that by looking at this prefix overlap, it can say, even though this application is not the least busy, it's got more tokens in its KV cache than application 2, because of this prefill overlap, this prefix overlap, the prefill will be faster, and hence it would actually be better to send it to this application here, application 3. And so that's the sort of decision making that you can have in the load balancer, a complex decision making, if your inference engine reports the right metrics and you have a system that's set up to use those metrics in decisions like load balancing. And the same metrics can be used in things like auto scaling and other sort of optimizations like that. So scrolling back, what have we covered today? So today we looked at why you should care about load balancing, why it's important to not waste resources and to give the best possible experience to your users, why traditional load balancing fails because of the variable compute required for different requests, as well as the traditional metrics used in load balancing being uncorrelated to LLM load, and then how to build an LLM-aware load balancer based on metrics reported like KV cache utilization and overlap between the prefix in the request and the prefixes currently saved in a model's KV cache.